welcome back. Today we will solve two more questions from the chapter Waves. Previously we have solved all of these questions from this chapter, and in the syllabus we are here right now. So in this video we will solve two questions to understand all of these objectives. So all of these concepts, the first one, the definition of intensity as power per unit area, and the second question will be targeting these concepts in the syllabus. We have covered all of these topics previously. If you haven't watched those videos, I would recommend go back and watch these videos for full understanding of this chapter. Okay, let's start with our first question. So a beam of light from a torch with power P is shown onto a surface. The light is spread over a circular area with radius R. Which of the following gives the intensity of light on the surface? I just showed you that intensity is defined as power per unit area, right? So this is one of the concepts in the syllabus that you should be able to use this equation. And it's very simple. Power is just P. Area, because it's a circular area, it will be area of a circle, which is pi r squared. So the correct option is D. But maybe in some other past paper question, the question from this equation or from this concept will not be as simple as this one. So you have to remember that intensity, because it is defined as power per unit area, it will have units watts per meter squared. So sometimes they will not mention that some quantity is the intensity of light. They'll just say that the power radiated per unit area is 17.6 watts per meter squared, right? So you have to understand that if the units are watts per meter square, they are talking about intensity. So I think I have seen some of the questions from past papers from this topic, which are a bit more complex, but for this lecture, I couldn't find those questions. So I just had to pick this basic question. This second question, on the other hand, is a bit more complex and interesting. It is interesting because it allows me to target all the important concepts that I want to explain in this video. So let's start with a short review of all the concepts that we need to solve this question. And I want to emphasize, we only need a single equation to answer all the questions from this topic of refraction. And the equation that we need is Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. Now, you might be thinking that how is this possible? We need some other equations, for example, for critical angle, for refractive index, for speed of light and wavelength in different mediums. If, for example, someone asks you to find the wavelength of light in water, right? But believe me, this is the only equation we need to answer all of these questions, because all the other equations can be derived from Snell's law if you understand the definition and different concepts about light. You will see in a moment. Okay, first of all, I want to be very clear about which medium we will call 1 and which medium we will call 2. For example, N1 and N2, right? So for this, you have to remember that if, for example, we have two mediums, air and water, and the light is, let's say, coming from air and entering water. So basically like this, and because the density of water is higher than air, the light will bend towards the normal. So this is another concept that you need to remember or understand, that whenever the density of the medium is higher, light will bend towards the normal. Another thing that you, I think most of you already know about this, but still, just to explain everything, this normal line is always perpendicular to the surface. So make sure that you understand this point. You always have to draw the normal, and the normal line should be perpendicular to the surface. In this question here, you can see that the normal line is tilted because the surface is at an angle, but the angle between normal and the surface is still 90 degrees, which means that the normal is perpendicular to the surface. Okay, so our normal is perpendicular to the surface. Second, our diagram is correct because water is more dense, so the light bends towards the normal. This will be called theta 1, and the refractive index of the first medium will be called n1, and refractive index of the second medium will be called n2, and the angle of refraction will be called theta 2. And we called it 1 because the incident ray of light is in the first medium and the reflected ray is in the second medium. Now if I draw another ray of light, but this time the ray of light is, let's say, coming from the water and entering or emerging into air. This time, because the density of air is smaller than water, the light will bend away from the normal, so it will go like this. Now what you have to understand is that for this ray of light, because the incident light is in the water, that's why this medium will be called the first medium, and therefore the refractive index of water will be n1, this angle will be theta 1, this angle will be theta 2, and the refractive index of the second medium will be n2. This is very important because a lot of students make this mistake. They write Snell's law and they rearrange it for whatever they are trying to find, but in the end they will put, when they have to substitute the numbers, they will substitute in the wrong variables. So it's very important to understand that this medium on the left side of Snell's law is the medium of incidence, or the first medium from which the ray of light is entering into the second medium. Now we want to see how we can find the other equations from Snell's law. So first of all, if you are given angle of incidence and angle of refraction, and you want to find the refractive indices of the medium, you can simply rearrange this equation. The equation will be n1 over n2 equals sine of theta 2 divided by sine of theta 1. So this is the equation. If you are given the angles, for example, for angle of refraction, angle of incidence, you can find the ratio of refractive indices. In case of air, for example, n1 is just 1, right? So if you want to find the refractive index of water and you are given the angle of incidence and angle of refraction, you can rearrange this equation for n2. n2 will be sine of theta 1 divided by sine of theta 2. So you see, this is the equation that you see sometimes for refractive index of any medium, defined as sine of angle of incidence divided by sine of angle of refraction. But this is not a new equation. You don't have to understand or memorize it separately. It is just derived from Snell's law. So if you understand Snell's law and you know which one is, which medium is 1, which medium is 2, you can very easily derive this equation for refractive index in terms of angle of incidence and angle of refraction. And make sure that you don't forget that the original equation is this one. So we still have n1 here in the denominator. The reason that we don't write n1 is because the refractive index of air is just 1, right? So if you have, for example, a different medium, for example, honey and water, right? So in this case, you need to write the refractive index of honey, and then this equation will give you the right answer. So make sure you understand that there is always n1 here in the denominator, because we are still working with Snell's law. And if, for example, you have some other medium, some medium other than air, then this n1 will have a different value. It will not be just 1. Let's move on to the next topic, which is critical angle. So first of all, I want to write a definition for critical angle, and then we will see how that definition allows us to calculate critical angle from Snell's law. Critical angle is defined as the angle of incidence for which the angle of refraction is 90 degrees. So critical angle is the angle of incidence for which the angle of refraction is 90 degrees. Now what this means is, let's say if you have two mediums, again water and air, and for reference we draw normal to the surface. So we have a ray of light coming from water and entering into air, and because air is lighter, the light will bend away from the normal. Now because the light always bends away from the normal, you can guess what will happen if I increase this angle of incidence, or theta 1, right? So if I keep on increasing this angle of incidence, what will happen is that this angle of refraction or theta 2 will keep getting bigger and bigger, and there will come a point for angle of incidence for which the angle of refraction will just be 90 degrees. So the refracted light will just go along the surface, right? So this angle of incidence, theta 1, or sometimes we call it theta I, and this angle of refraction is theta 2, and you can see this theta 2 is 90 degrees. So by definition, when the angle of refraction becomes 90 degrees, the angle of incidence, whatever the angle is, it will be called theta C, which is the critical angle, right? So I hope this point is clear. Now, if you read the definition again, you will understand this equation in a better way. So again, theta C, critical angle, is the angle of incidence for which the angle of refraction is 90 degrees. Now, let's go back to Snell's law and see how will the Snell's law change. So we have N1 sine theta 1 equals N2 sine of theta 2. Again, this side is incidence, this is refraction. Now, if we apply this equation to Snell's law, we can write N1 sine of theta of incidence, but now the incidence angle is critical angle, so I'll write theta C. And by definition, because the incidence angle is critical angle, the refracted angle will be 90 degrees. So theta 2 should be 90 degrees because this is the definition of critical angle. If the angle of incidence is the critical angle, the refracted angle should be 90 degrees. And we know that sine 90 is just 1, right? So sine of 90 degrees will just give you 1. You'll get N2 here, N1 here, and you'll get sine of theta C. Now, if you just rearrange this equation for theta C, I'll do it in steps. So first of all, sine of theta C will just be N2 over N1. We divide both sides by N1. That's how you get this equation. And now, because we need to find theta C, we can take sine inverse on both sides. On the right side, sine inverse and sine will cancel. And on the right side, you will get sine inverse of N2 over N1. Again, you have to remember which medium is N2, which medium will have refractive index N2, and which medium will have refractive index N1, okay, according to the convention that I explained at the start of this video. So that's it. This is the definition of critical angle. And if you are given the angle of refraction, the angle of incidence, you can very easily find the critical angle again using Snell's law. There is no new concept here. This is not a different equation. You can derive it from Snell's law if you understand the definition of critical angle, which I've written here, and if you understand which medium is the first medium and which medium is the second medium. A very important concept that I forgot to explain here is that this critical angle only exists if the light, or if the incident light, is coming from a denser medium and it is entering into a lighter medium, okay? Only if this is the case, then you can work with critical angle and you can use this definition. If, on the other hand, the incident light is coming from a lighter medium and entering into a denser medium, then this definition or this whole concept of critical angle, it doesn't mean anything, okay? Because the reason we define critical angle is because if the angle of incidence is greater than the critical angle, then you will see total internal reflection, which is our next topic. So if total internal reflection does not occur, then it's meaningless to define critical angle, right? So this is very important to understand. And this next topic is total internal reflection. Let me write it here. So what happens in total internal reflection is, again, you have two mediums, let's say water and air, and this is our normal. The incident light is coming from a denser medium, which is water, and it is entering into a lighter medium, in this case air. And let's say for some angle, the angle of refraction becomes 90 degrees. So if this happens, we know that this angle must be critical angle. So we will call it theta C. And this angle of refraction is 90 degrees. Okay, now what will happen if I increase the angle of incidence and it becomes greater than the critical angle? Okay, I will draw it in a different color. So now this line, you can see it makes an angle which is greater than the critical angle, right? So the angle of incidence is now greater than the critical angle. What will happen is that the refracted ray will be refracted in the same medium like this. This is called total internal reflection. All of light will get reflected back in the same medium. And this only happens if the angle of incidence theta I is greater than the critical angle theta C. If this is the case, the result will be total internal reflection. Now again, like I just explained, for this phenomena to occur, total internal reflection, there is a specific condition, and the condition is that N1 should always be greater than N2. What it means is that the refractive index of the medium of incidence should always be greater than the refractive index of the second medium. If this is not the case, so if this is not true, then you cannot have total internal reflection, and then it will be meaningless to define critical angle, right? So that's why I explained that if the light was coming from air and entering into water, then because total internal reflection is not possible, because N1, which is in this case, it will be the refractive index of air, it will be smaller than N2, right? So it means total internal reflection is not possible, and then it is meaningless to work with critical angle. So all of these things are connected, and you have to remember that you can derive critical angle from Snell's law. Now, finally, the last thing that you want to understand for these, for any question from these topics, is how the speed of light and how the wavelength of light are related to the refractive index N. And I'm thinking I should make a separate video for this concept, because this video is getting a bit longer. But I want to write the equation nevertheless with these concepts. So the equation is that N1 over N2 equals lambda 2 over lambda 1 equals V2 over V1. So this is the last equation that you need to solve any question from the topic of refraction. And I wanted to explain all of these concepts in a single lecture, because all of these things are connected, right? So you can see critical angle, total internal reflection, index of refraction, all of these concepts are connected to Snell's law. And this is always a good strategy. If you are learning 2 or 3 concepts that are connected, make sure you always learn them together. If you learn them on different days, for example, you might think, for example, that, for example, this equation for critical angle is some new concept that you have to remember apart from Snell's law, which is not true, right? It is just, you can derive it from Snell's law. All that you need to understand is Snell's law and the definition, for example, of critical angle and how we define first medium and second medium. Okay, now finally, let's see if we can apply all of these concepts to answer this past paper question. You can see it has 4 points. And the question is, a ray of light enters the diamond along the normal at point Y as shown. So you can see the normal line is like this, and the ray of light is entering along the normal. The ray is incident at the diamond air interface at X with an angle of incidence equal to 40 degrees. Again, I hope you remember that we have to measure the angle of incidence with respect to normal, and that the normal is always drawn perpendicular to the surface. So this dashed line is the normal, and this is the angle of incidence, and it is 40 degrees. The question is asking us to deduce whether the ray follows the path at X as shown. And the path that is shown as point X is this path right here. So I will give you some time to think about this question. You can pause the video, see if you can solve it. I will give you a hint. You have to rephrase this question in some other concept, in terms of some other concept that you already understand. So you can see that the ray of light got reflected inside the diamond, right? This is called total internal reflection. So the question is basically asking to deduce whether total internal reflection is possible or not if the angle of incidence is 40 degrees. And you can also see that speed of light in diamond is given, right? So just because they have given us the speed of light in diamond, we know that we have to use this equation. because this relates the refractive index with the speed of light in diamond. But we, at the same time, we also need to figure out whether this angle of incidence, which is 40 degrees, is it greater than the critical angle theta c? Because like I explained, for total internal reflection, the angle of incidence has to be greater than the critical angle theta c. If this is true, then the light will get reflected inside the same medium. So let's see, first of all, if we can find critical angle. We know that the critical angle is given by sine inverse n2 over n1. But the problem is that we don't know what n2 and n1 are in this question. And for this, that's where our second equation comes in. n1 over n2 is given by v2 over v1. Here in our equation for theta c, which is the critical angle, we need sine inverse n2 over n1. So if I reverse this, if I take the inverse of this equation, I will get n2 over n1 equals lambda 1 over lambda 2. By the way, we don't need wavelength in this question, but just still so that you remember that the relation between wavelength and velocity is the same for refractive index. And we will get v1 over v2. Another important thing to remember is that these numbers here, they are always opposite. So if you have n2 over n1, the ratio of the velocities will be v1 over v2. So here we need n2 over n1. If I want to write it in terms of velocity, I will write v1 over v2. And now you will realize why I emphasized so much about first medium and second medium, right? Because a lot of students make this mistake. They write this equation, but they don't know what is the speed in the first medium and what should be the speed in the second medium. Now, if we go back to the diagram, we know that the incident light at point X is this one, and this is in the diamond, right? So this is N1, and similarly, the speed of light inside the diamond will be V1. And this was our second medium, supposed to be our second medium, in which the light was supposed to exit. And therefore, the speed of light in air will be n2, which is just the speed of light c. And the speed of light in diamond is given, it is different from c. The speed of light in air is 3 times 10 to the 8 meter per second, but the speed of light in diamond is 1.25 times 10 to the 8. Now, if you substitute these numbers and take sine inverse of the ratio, you will see that the critical angle comes out to be 25 degrees. Now, if we go back to the question, when we rephrase the question was basically to deduce whether total internal reflection is possible or not if the angle of incidence is 40 degrees. And we argued that by definition, if the angle of incidence is greater than the critical angle, then total internal reflection will happen. So we saw that the critical angle for diamond, we just calculated it, was 25 degrees. And the angle of incidence is greater than the critical angle. That's why total internal reflection will happen, and this path of light is correct.